And now for advanced beer pong. We're at the same party. Okay, so we've got a cup 0.2 or 20 centimeters high, 1 meter away, but now a frat boy is throwing the ball. And he's throwing it from 0.6 meters because he's, a little bit taller. And he's throwing it at 5 meters per second because he's a frat boy. See, my narrative is consistent here. And he also wants to land it in the cup. And the question is, if he really has to throw it at 5 meters per second, what angle should he throw it at? That's what we're going to solve. So here is my advice to you. If Vi or theta is, what's the word I'm looking for, is left variable, is unknown, use R. So in beginner's beer pong, I said this is a case where you don't want to just write out the R vector. You want to just kind of solve it by breaking it in half. But when these are unknown, R. Okay? So we'll do it the proper way. We will write the position vector R of the ball. Right? We just need the x component. Well, x component is constant velocity motion, no acceleration, so it is simply 5 cosine theta t. No initial position I hat, right? Because it started at 0. There's the origin. And the y component. The y component did start at 0.6. It has an initial velocity 5 sine theta t. And of course in the y, it's accelerating down minus 1/2 gt squared, or minus, I'll save myself some math, 4.9 t squared. That's 1/2 of gravity, 4.9. All right. So now what you can do when you have something like this is you can say it must be at x equals 1, y equals 0.2 at some time. So we just have to solve these in this case, and I'll probably call it t star since it's a specific time. So for example, 5 cosine theta, a specific time t star, has to be equal to 1 meter. And at the same time, y, 0.6 plus 5 sine theta t star minus 4.9 t star squared has to be equal to 0.2, the height of the cup. It has to be right here at 1.2 at time t star. So what we have here is 2 equations. All right, there's an equation, and there's an equation, and 2 unknowns. We don't know theta, and we don't know t star. Of course, what we want to solve for is theta. So in this case, it looks bad. It's not as bad as it looks. We're going to solve this one for t star. T star equals what? 1 over 5 cosine theta. And we're going to plug that into there. So what do we get? 0.6. I'm going to go ahead and bring this 0.2 over. So this 0.2 is going to come over here. I'm going to get 0.4 plus, let's see, this is going to, the 5 over 5 is going to cancel. Sine over cosine is tangent theta. So when you plug that in there, you get just tangent theta. Promising. And then you say minus, now we've got 4.9 over 25 cosine squared theta. 4.9 over 25, that's about 5 over 25, that's about 0.2. So this one is minus 0.196, close to 0.2. And then we just have this 1 over cosine squared theta in the bottom, times 1 over cosine squared theta. Sorry. Too much beer pong. There we go. Equals 0. All right. And that looks pretty hopeless. We got to solve this for theta. We got rid of the t star. Got to solve that for theta. Well, sometimes when it looks hopeless, you got to go to your trig identities, right? So there is a trig identity, and you could prove it to yourself pretty easily, actually. That 1 over cosine squared theta is equal to 1 plus tangent squared theta. And if you don't believe me, just think, what if we multiplied through by sine squared, or by cosine squared? If we multiply this through by cosine squared, this would be 1 equals cosine squared plus sine squared, right? Sine over cosine, cosine, which we know, sine squared plus cosine squared is 1. So it's really just a modification of that. So if we're going to use that, what that means is we're going to turn 1 over cosine squared theta into 1 plus tangent squared theta. So this is going to become 1 plus tangent squared theta, which means we're going to have 1 times 0.196. So that negative 0.196 we can combine with the 0.4. Okay, so the constant terms are about to change to 0.204. Okay, I'm not messing with that term, plus tangent theta. And then the squared term was this is minus 0.196, and then this part. Minus 0.196 tangent squared theta equals 0. Okay, and now that is a nice little quadratic equation, right? Tangent squared theta, tangent theta to the 0. So even though it's tangent rather than x or y, you can still solve it, quadratic equation. And what you'll get if you do that, so you go, oh my God, I could write it minus 1 plus or minus the square root of b squared 1 plus 1.6 is the minus 2ab over 2a is whatever it is, over 2a is minus 3.392. What you're going to get is that theta, of course, has two values, right? There's a plus or minus in here, so you get that theta equals either 81.5 degrees or it equals negative 57 degrees. Okay? So when you get two answers in a physics problem, sometimes one of them is meaningless, and sometimes they actually both work. So let's look at this case. What do we think it is? It could be 81 degrees above the normal. You got to throw it at a huge angle. That seems all right. But maybe the negative 57 is also right, because you could throw it like that. So in this case, both answers are actually correct. So first, let's see the high answer. Does that really work? Let's see what can happen here. So fretboard, I'm going to throw it really hard. I'm going to throw it up and up. Oh, no. Oh, I forgot the rules. High angle. We got to get the high angle. This is not over. See that? You see that? Oh, man. It was, I don't know what that was. Something weird. So at the high angle, it will go in, as you can imagine. You just got to get the hang time right for the thing going down, right? The low angle. Can the low angle go in? I don't need this. I'm just going to nail it. Oh, I'm not. Oh, 57 degrees. I thought it was 37. I was, 57. Oh, here we go. Okay, this is the last one. So this has to go, or I'm just going to cancel the whole class.